Okay, the first thing that I want you to notice on this page, under the objectives, it says memorize key ions and atoms. And it says you must score a 95 out of 100 to receive credit. So this weekend on Schoology, I am going to post the polyatomic ions that I need you to memorize. There's about 20 of them. They'll be through Quizlet, so you can do flashcards. Now, I'm going to tell you that the sooner you do this, the easier it is for you. I don't actually record your score in the grade book until you get a 95. I don't give you the same quiz, right? So say you get an 80 on the first one. I'll give it back to you. You can study the ones you got wrong. I'll mix them up again. Some of them I'm going to give you the name and you have to write the ion. Some of them I'm going to give you the ion and you're going to have to write the name. Now when you write the ion in the chemical formula, like say it's sulfate, you have to write SO4 minus 2, so you have to write the charge. And the reason that I have you do this is because at the college level, when we start writing problems, a lot of times you're given the names. It'll say sodium carbonate and silver nitrate. And that's all they're going to give you are the words. You have to put that into chemical formulas, complete the reaction, and then we might have to do some dimensional analysis to figure out if I start with this many grams, how much is going to be produced. If you have to stop and you have to look up every single ion, it will take us forever to get through a problem. So the good thing about this, it's for your benefit, and I give you the entire first semester. So I give you until January to get your 95, but I'm telling you that the sooner that you learn them, the easier it becomes for you in class when we're doing work and we're doing problem solving. So if you score poorly on the first one, it doesn't matter. It doesn't go in the grade book till you get the 95. This is purely for your benefit. So we're going to spend the first couple of pages. Now notice the top of this says chapters 1 through 3. I am giving you the highlights of chapters 1 through 3 because honestly, it is a review of the most rudimentary concepts that we learned in Regents chemistry. And you're probably going to be like, is she really asking us that at the college level? Well, because you have to realize that when most students take college chemistry, they had Regents chemistry, they had Regents physics. Now they're in their first year of college. So they skipped a year. So we go back to the basics and we just review some of the important things. I'm also going to put up on Schoology the SUPA PowerPoints. Remember I told you those PowerPoints are a little bit more in depth. Okay, as I was saying, I am going to post SUPA's PowerPoints for chapters 1, 2, and 3 this weekend. I don't think that there's anything in there that you will have to be like hardcore studying. What I would just do is breeze through them. Just breeze through oh yeah, I know that. Yeah, oh, I know that. Yeah, I know that. If there's anything that you come across in chapters 1 through 3 that you don't know or you feel you need a review on, at our next block period on Tuesday, I want you to make a note of that and we'll talk about it. Okay? To review there, you see we have a breakdown of matter. And on the right-hand side, it's really like a nice branching tree. What is matter? What is matter? Something that takes up space, yes. And all matter has what?
Properties.
Okay, but what's one key component of matter? Mass, absolutely. So, takes up space and has mass. The first thing that we're looking in there is pure substances versus a mixture, okay? What are pure substances? An element is a pure substance. And what else is a pure substance? Compound, okay. Elements and compounds are pure substances. So I want to talk about that for just a second. So if we talk about an element, what do we know about an element? It can't be broken down. Okay, absolutely. So I'm not gonna write all this. If you feel that you need to write it, you can write it. You know what you know and what you don't know. What about a compound?
Can be broken down.
It can be broken down. Physically or chemically?
Well, no, chemically.
Chemically. Because the real definition of a compound is two or more elements chemically combined. So if something combines by chemical means, it can only be broken down by chemical means. Give me an example of an element. Okay, carbon, copper, good. Give me an example of an element that appears as two atoms. I don't want to give you the key word. What elements appear as two atoms? They're not found alone. Diatomic elements, yes. What are our diatomic elements? Brinkelhoff, yes. So when we talk about elements, I want you to realize that our diatomic elements, our Brinkelhoff, are part of elements, okay? And then we have our monatomic elements, our single elements, which would be like the carbon and the other ones that we talked about. What about an example of a compound? Water, H2O. Give me another example. What was that? CO2. All right, so the H2O and CO2 are examples of what? What type of compounds? What type of compound? Think about what they're made of.
Oh. That's the word. It's like metals.
Okay, well, they're not. They're two nonmetals, right? So what kind of compounds are two nonmetals? Covalent. All right? So covalent compounds, two nonmetals. Give me an example of an ionic compound. You use it on every day on your food.
Salt.
Salt.
NaCl.
NaCl, sodium chloride, good. So remember, our ionic compounds are metals and nonmetals. Just reviewing here, okay? All right. The other thing that I want to talk about is when we talk about elements and compounds, right? We said they are pure substances. If they're pure, that means that they're consistent throughout. So what's another word for something that's consistent throughout? Homogeneous. So I want you to realize, although elements and compounds are pure substances, they are also homogeneous. All right? So going on to the next page, we talk about the difference between homogeneous and heterogeneous. Homogeneous means consistent throughout, as we just said, or the same throughout. What would be an example of something that's homogeneous? Salt water, absolutely. What else?
Our milk nowadays.
Milk is homogeneous, okay? Even soda before it's unopened is homogeneous, okay? Okay. One thing that I want to mention is that all solutions are homogeneous. So please remember that. All solutions are homogeneous. So when we talk about NaCl aqueous, or we talk about C6H12O6 aqueous, or we talk about soda, those are all solutions. They're all homogeneous. Opposite that, we have heterogeneous, not consistent throughout. So what are some examples of heterogeneous materials? Cookie dough. What else?
I would say pizza, like pepperoni
Pepperoni
pizza.
pizza. You know my favorite, cat vomit.
I haven't seen
Oh
it
my
yet.
god.
Oil and vinegar. Sand and water. Rocks, soil. All of those are heterogeneous. Now, remember that when you have a mixture, any mixture, whether it be homogeneous or heterogeneous, are two or more substances physically combined. So if they're physically combined, that means that we can separate them by physical means. So all mixtures can be separated. And some of the ways that they can be separated are listed here. Okay? We have distillation, chromatography, solubility, and some others. We're going to talk about that in just a minute. Okay. So, to review, distillation is separation by boiling point. Chromatography, I am going to write this one down because you should know what it is, and we haven't really talked about it. We mentioned it in, it's separation of a mixture using a mobile phase and a stationary phase. And I'll explain that a little bit more in just a minute. So the movement of the particles in a chromatograph are based on that substance's affinity for either the mobile phase or the stationary phase. And what I mean by that is, if you recall, when you did chromatography in 9th grade, you put these pigments on the end of a piece of paper. That was the stationary phase. Okay, they were fixed on the paper. You then put your paper in a mobile phase. You put it in a solvent. That solvent can be water. That solvent can be alcohol. Okay? The solvent is really going to depend on the nature of whatever the stationary phase is. Obviously, if you have a non-polar substance that's stationary, you're going to need a non-polar mobile phase or a non-polar solvent. If you have a polar stationary phase, then you need a polar solvent or a polar mobile phase. So as particles travel, some particles move further than others up the chromatograph. And that's based on whether they have more of an affinity for the mobile phase or the stationary phase. Some of it can also be due to particle size. Particle size. Smaller particles tend to move further. Okay? Other particles that are bigger tend to move less distance. We're actually going to do a lab this year where you actually calculate the distance of particles that move and try to identify which ions they are. All right, what is solubility? No. What does the word soluble mean? Okay, how much of a substance dissolves in a given volume, and what else is important? What variable will depend on how much dissolves? Temperature. Remember, recall in your head table G. As we increase the temperature for solids, solubility increases. As we increase the temperature for a gas, solubility decreases. Okay? Now, under others, I heard it mentioned right from the beginning, filtration. Yes, that is also another way to separate by physical means. What else? There's another one that we did. Think about how you would separate salt water. Okay, so what do we call when we boil something? Evaporation. Because we're not separating by boiling point. If it, right, you're evaporating the water. You're inducing evaporation via heat. Remember, in distillation, you need to have two or more liquids that have different varying boiling points, like we did with the water and the alcohol in one of our last labs. Okay. Good so far? It's all coming back? You're just taking the respective notes that you need. This is not like Regents Chem where you write down everything. You write down what you need, because what you need and what you need are two different things. Okay. We're going to review significant figures. Why do we have significant figures? Does anyone know why they even torture us with them?
Like accuracy, like how much or something, like when you're taking measurements.
I'm going to ask you that this way. If I gave you each something to measure, would you all get the same thing?
No.
No.
No. So the reason why we need significant figures is because every measurement, no matter how careful someone's being, is going to have some degree of uncertainty, because that very last digit is always an estimate, right? If you have a graduated cylinder, let's say, that goes up by ones, right? What if the meniscus is between two lines? What do you have to do? You have to estimate. What I estimate and what you estimate are going to be two different things. And point in case, right now I'm teaching the lab for this class over at the college. So last night I was doing a lab that you're going to be doing probably next week, and two groups measured the length of their lab book and got the same measurement, and one got 1/8 of an inch greater. So I went to that group because I knew all the textbooks were the same, and I said, can you show me how you measured? So they did, and they're like, well, we didn't know what that little line was because it wanted you to measure it in inches. So it was really 10 7/8. So they just rounded it to 11 inches. I was like, you can't do that. But my point is, they got different measurements. So we need significant figures because that last digit is always an estimate. All right. I am not going to go through, if you want me to go through the whole Atlantic Pacific, I will. But this is pretty straightforward. All non-zero numbers count. Okay, so integers count. Leading zeros don't count. Trailing zeros only count if there is a decimal. 3 simple rules. So, do me a favor right now. I want you to throw out some numbers. Throw out some numbers to me.
72.
Okay, is that with or without a decimal?
72.894.
72.894. I need another number. Somebody else.
0 to 400.
0 to 400. You want a decimal before the 2 or no?
Sure.
Okay. Give me another one. 0.0 what? 3. All right. All right. So I added 2. So let's go through these. 5 examples. The first one that Gabe gave us, how many sig figs does it have?
3, 5, 5. All of the numbers.
Okay, so, yep, look at rule 1. All non-zero numbers count. So this one has 5 sig figs. Okay. What about the next one?
2,
4.
4. Okay, rule 3. Trailing zeros count if there is a decimal. So we have a decimal here, so that means that those trailing zeros count. Okay? What about the next one? 3. Because of rule 2, leading zeros don't count. What about the next one, 20? 1. There is no decimal. Rule 4. Trailing zeros don't count if there is no decimal. And the last one?
6.
6. There is a decimal, so all zeros count. Make sense? Yes? Okay. Do you need to write down those examples?
Yeah.
Okay. So take a minute if you need to write down the examples. Then we're going to review the addition and subtraction, multiplication and division. And then I'm hoping to review some dimensional analysis. Okay? I am going to post the problems on Schoology for however far like we get so that you can start working on them. Well, I'll post all of them and I'll put a marker. These are the ones that you should be able to do what we got up through in notes, okay? If you want to go ahead, that's up to you, all right? All right. Let's just review the rules first. In addition and subtraction, as always, with anything, you do the math first. Just do the math. Then, once you have your whole answer, you're going to present it to the least accurate place value. I used to say the least number of decimal places, which is the same thing because the 10th place is less accurate than the 100th place. But for Regents kids, it's easier to say the least number of decimal places than the least accurate. A multiplication and division, same thing. We do our math, and it's going to be to the least number of significant figures. All right, so I'm going to put up a couple of examples here, and I want you to solve them, and let's see how we do. All right, so I gave you 4 problems.
Is there a point between the 2 and 3 for a decimal?
Yes, it's 23 right here.
No, not that one. Between the 2 and the 3 on the first one.
No, it's 23.
Okay.
It's just 2, 3. I'll try to make these bigger so you can see them. I haven't written with the stylus all summer, so it's I got to get used to the pressure again. Like I feel it's like dragging on the screen. picked these problems because some of them look, they're more challenging than they look. So I wanted to make sure I cover all bases. Also, I need to know who does not have a scientific calculator, like a TI-83 or whatever.
I do, but not.
Okay, you have one? Okay. Do you have one? Okay.
This one, like this?
No.
What?
Like one of these.
Oh, no, but I can get one. Where would I get them
No, no, no. I will loan you one.
from? Okay.
I will loan you one. I just don't have, I don't know if I have batteries with me. These might all be dead. Yeah. All right, I will give you one on Monday. I have batteries at home, okay? And then I'll just sign it out to you for the year. And you have one, you said? Okay. I have plenty to loan out. Nobody needs to go buy one.
I probably just got wrong. They were too easy.
All right, when we do the math, not your answer, when we do the math on the first one, what do we get? Okay, we get 24.2. If we follow the rule, what does my answer have to be? Exactly. So least amount of decimal places, my answer has to be 24, because 23 is to the ones place. There are no decimal places, so that would be least accurate. On the next one, 2.56 minus 1 is what? 1.56, yes? Okay. And I have to be to what place? My answer, 10th place. So what's my answer going to be? 1.6. Excellent. All right. Multiplication. When I just do the math and I multiply, what do I get? 23.2928. 23.2 has how many decimal places? I mean, how many sig figs? 3. And 1.004? 4. So my answer can only have 3. So my final answer is, yes, 23.3. Good job. Didn't trick you guys up yet. Maybe on the last one. 15.67 divided by 0.0062. You do the math. What do you get?
405,046.
Whoa. When you divide? Yeah. 2005.7.41. All right, that's far enough. All right. So 15.67 has how many sig figs? 4. And what about 0.0062? 2. My answer can only have 2 sig figs. 2,500 with no decimal is acceptable. It is not the answer that I would have chose, but it is acceptable. There's no decimal, so that only has 2 significant figures. What was another way that we could answer this? What's another way to represent 2,500, which is what I did? Huh? 2.5 e to the third, right? Or times 10 to the third. I just use e because it's easier. But you and I came up with the same answer. Good job. All right. Feeling the review there? Is it all? We
The 27 like that? Yeah.
due to significant figures, yes.
All right.
Yes, due to significant figures, yes. We're dusting off all the cobwebs. That's the important thing. Dimensional analysis.
Oh boy.
Oh, come on. Where's your excitement?
Oh, what this is.
All right. So, remember, dimensional analysis is simply conversion factors. 1 dozen, 12 eggs. 1 foot, 12 inches. 1 centimeter, 2.54 centimeters, 1 inch, right? Can flip them, whatever you want on the top, whatever you want on the bottom, so that your units cancel out. We're going to talk about several types of problems: one-dimensional, multi-dimensional, triple-dimensional, and complex. We're going to cover it all right? I gave you today, because I'm that kind of teacher and so nice, a conversion chart to help you, especially when you're doing your homework. It saves time in having to look up things, all right? You will not be able to use it on a test, okay? But it's right at your fingertips now for what our practice is and for what you need to do for homework. And I'm not going to ask you anything on a test or quiz that's going to be outrageous. If I think it is, I would put the conversion factor on it, all right? I'm not testing whether you can memorize 25 conversion factors. I'm testing whether you understand the process of dimensional analysis to convert one set of units to another set of units. Simple as that. All right, so let's try a simple one-dimensional problem, all right? Baby steps. I want you to convert 12 feet to centimeters. Okay? Setting up your railroad tracks. Now, you see how they do times in between on the example? That's where I put I just put the slash. So they do it like this: conversion factor times conversion factor times. I do it like this, okay? I don't care however you do it. It's the same thing. This break means times, all right? However you feel more comfortable. So you're converting 12 feet to centimeters. See if you can do it, and then we'll go over it. I wrote this on the right-hand side because I had forgot to start recording. To keep my focus, I know that I have to wind up with meters per seconds. Now, I can choose to convert the miles first, right? So if I choose to convert the miles first, then miles is going to be down here, and I'm going to do that first till I wind up with meters in my numerator. Then, once I have meters in my numerator, I'm going to go back and I'm going to convert the hours, okay? So I want you don't have to start with miles. If it's easier for you to convert the hours first, you can convert the hours. So do you want to do one together? All right, so what do you want to start with, miles or hours? You tell me. Huh? Miles? Okay. So what is a conversion factor that we can use from your sheet with miles?
5,280 feet.
No, we need something, but we don't have feet here. Do we have miles and kilometers on there? 1.609 what? Miles? So 1.609 kilometers is 1 mile, right? Miles cancel, right? But I don't want kilometers, I want meters. What is my relationship between kilometers and meters?
The conversion factor of 1,000.
1,000, yes. So one kilometer is 1,000 meters. So my kilometers cancel. Notice now I've got meters. So I've got my unit in my numerator done. Now I want to go back and look at hours. What is a conversion factor between hours and some unit of time that we know? Is an hour. Okay, good. So 1 hour is 60 minutes. I'm not there yet. I need seconds. So what else do I know? 1 minute, 60 seconds. So notice hours cancel, minutes cancel, and notice that the unit in my denominator is seconds. So now I have my unit in my numerator and my unit in my denominator. Everything else is math. I'm going to multiply everything in my numerator, 55 times 1.609 times 1,000, and then I'm going to divide it by everything in my denominator, which is basically 3,600, because 60 times 60 is 3,600. And then we will have our answer. So when somebody gets that, let me know what you get. $24.58. Can anyone convert that? Confirm that. That's not what I got.
24.58.
Yeah,
That's what I got.
it is?
Yeah.
Oh, yep. I pushed something in. You are correct. So 24.58 meters per second, all right? I don't want to go on to type 3, okay? I want to do another one of type 2, and then we'll stop there, because the type 3 get a little bit more involved. So I think there's a place for you to go more toward the bottom of your page. Is there room?
Yeah.
Okay, maybe you can put another one. So let's try converting. Let me see if I have a conversion chart in front of me. Pick something. I'm actually going to pull one out of the book. These are a little bit harder to make up out of my head. Okay. 9.58 seconds per meter. 9.58 seconds, per 100 meters. So this is a world record for the 100 meter dash is 9.58 seconds. So we have 9.58 seconds per 100 meters. And I want you to try to convert that to I want you to convert it to two things, feet per second, and I also want you to convert it to kilometers per hour. So you're converting it twice. You can do them separately. So convert seconds per 100 meters to feet per second, and then seconds per 100 meters to kilometers per hour. So it's actually two problems. All right? So work on that.
Route 17 is at the end of the lineup.
So flip it to start. Meters, 9.58 seconds. Okay? Perfect. Because that's what dimensional analysis is.
And could you also just keep it like that, do dimensional analysis, and then your answer is that?
Well, no, because it'll be that way. I asked you to present it in feet per second, so you're going to want seconds on the bottom. That was your first clue to flip the original that I wrote down. And the second one in kilometers per hour, you want the seconds on the bottom too because you want it to change to hours. So you know what? Just try to finish up those two calculations and take a look at the videos, the PowerPoints that I put up. And then my lesson on Monday when I'm not here will continue. I will go over these in my lesson so that you'll see what you should have gotten, and then it'll continue.